So the first video was all about carbon and the different types of carbon and all that kind of stuff. But of course, organic chemistry isn't just carbon because carbon is pretty unreactive. And so if we didn't have any chemical reactions, there wouldn't really be much to talk about. So we're going to focus today, or this video is going to focus mostly on the other elements, right? Besides carbon, the potentially more interesting or more reactive elements that are in there. And so we're going to do that by looking at formal charge. So formal charge calculations, you guys know the formula. Um, you guys know the formula from general chemistry, right? So you can figure it out using unshared electrons, shared electrons, etc., and all that, valence electrons and all that other stuff. But the nice thing about organic chemistry is we're really only focused on this area of the periodic table, right? So that very top row of the periodic table plus hydrogen. Right? And what we find is that if we go across and number out the number of valence electrons, right? Oh, there we go. 4 valence electrons for carbon, 5 valence electrons for nitrogen, 6 for oxygen, 7 for all the halogens. I'm going to use fluorine here, but of course, fluorine, chlorine, bromine, as you go down the periodic table, each one of them is more or less the same. So we increase the number of valence electrons, we go across the group of the periodic table. And when we talk about formal charge, we can figure out pretty quickly that there are patterns for the number of bonds and the number of lone pairs for each one of these groups, right? Carbon, we've already talked about. Carbon likes to have 4 bonds and no lone pairs when it's neutral, right? And we said that that's one of the reasons that carbon's so interesting is because it has no lone pairs. It tends to be pretty non-reactive. Nitrogen, the next one over, to get to the full octet, has 3 bonds. 5 plus 3 makes 8. And then we have 1 lone pair. So each bond shares 1 more electron with the nitrogen. But in order to get to the octet, we have to have 1 lone pair there. The pattern continues. Neutral oxygen likes to have 2 bonds and 2 lone pairs. And fluorine likes to have 1 bond, or the halogens like to have 1 bond to them and 3 lone pairs. All of these considerations are for the neutral compounds. We will be dealing with some charged compounds here in a second. So this is all for neutral. So a neutral nitrogen will always have 3 bonds and 1 lone pair. And those bonds can be sigma bonds or pi bonds, doesn't matter. Now what's interesting is that, and then I guess I left off hydrogen here, but hydrogen likes to have 1 bond and no lone pairs. Right? Hydrogen will always be 1 bond, no lone pairs. So there's not really any variety to hydrogen. Okay, so what's interesting is that you'll notice that hydrogen and carbon have no lone pairs in neutral form, but all these other things have lone pairs. Right? And so we kind of group these things together. Hydrogen and carbon go on one side, and then we have all other atoms. And we call these heteroatoms. Because their electrons don't exist just in bonds, they have bonds and lone pairs. They get their own special designation. And the lone pairs are the interesting part, right? Because the lone pair kind of tracks with reactivity. So heteroatoms are basically anything that's not carbon or hydrogen. So you'll hear me use the heteroatom terminology. Anything that's not carbon or hydrogen is considered a heteroatom. So with heteroatoms, if you have more lone pairs than you would expect, more lone pairs than neutral, you end up with negative charge. Right? So if you have a nitrogen atom, we can draw a nitrogen atom really quick. If you have a nitrogen atom that has 2 bonds and 2 lone pairs, I don't even have to do a calculation. I notice that that's 1 more lone pair than neutral nitrogen usually has. That makes this a negative nitrogen. And you can imagine if you go the other way, if you have a nitrogen with 4 bonds and no lone pairs, that will go the other way, and then the nitrogen will be positively charged. So less lone pairs then neutral, just a positive charge. The good thing is that after you've done a bunch of this, you start to look at this, and a nitrogen with only 2 bonds to it starts to look pretty goofy. And so you think immediately, oh, there's something wrong here. This is not a neutral nitrogen. And two nitrogens with 2 bonds start to look like negative charge to you. Nitrogens with 4 bonds start to look like positive charge. And you just kind of start to associate that. So more lone pairs than neutral is a negative charge, less lone pairs than neutral is a positive charge. You can also do this with bonds, right? Like I said, nitrogen with 2 bonds is almost always going to be negative. Nitrogen with 4 bonds will always be positive. There is an exception. And the exception is carbon, right? Carbon cannot, of course, have fewer lone pairs. Carbon can't have less than 0 lone pairs. That's not allowed. And so we have this kind of special species, a carbon with 3 bonds and no lone pairs. Has a positive charge, is positively charged, and is called a carbocation. We are going to talk about carbocations forever. Really, carbocations are the main kind of link between where we start here on the very first week to all the way through to the end of Organic 2. So if you take this course and the next course, Organic 1 and Organic 2, we will talk about carbocations all the time. Okay, so this is interesting. We now have basically defined 4 different places where electrons can exist. 4 places for electrons. Okay. The first one that we defined is a sigma bond, right? A bond that connects atom to atom. We also had pi bonds, right? Any additional bonds beyond that first bond that exist. And then the third one is a lone pair. And lone pairs basically mostly have to do with heteroatoms, right? Heteroatoms tend to have lone pairs. Charged atoms can also have lone pairs. The last thing that tells us about where electrons reside is a carbocation. Right? And so a carbocation technically is not is the lack of electrons instead of talking about where electrons reside, but it does tell us where electrons aren't, and so we kind of connect these two together. So now all drawing of organic molecules is concerned with organic molecules is about representing where electrons are, right? This is the most important thing. So I remember, I'm going to switch this over because I'm just going to prattle on for a little bit here. I remember when I was in graduate school, I think this was my first year in graduate school. We went to one of the other students in the group. We went to his apartment and stuff, and we were just talking about chemistry because we're giant nerds, you know. And he was a third year or fourth year graduate student, so he had been in graduate school for a while, and he was in a very serious state, if you know what I mean. He was very earnest for chemical reasons, let's say. And he leaned across the table to me and said, "Man, at this point, I don't even see bonds anymore. I only see electrons." So that was goofy, but that's basically where we want to get to. Now, we probably don't need to be quite as um, under the influence as he was at that point in order to get there. But the idea is that that's what organic chemists, people who think about organic chemistry and do organic chemistry all the time, that's how they see structures. Right? They see structures as a representation of electrons and where those electrons are and also where they're going to go. So when we talk about resonance, when we talk about reactions and all that other kind of stuff, that's what we're going to focus on is where those electrons are and where they're going to go. And within 1 week, we already have, right, our list. These are the 4 places that electrons are going to be. These are the only 4 things that we're really going to worry about throughout this whole course. We're going to worry about sigma bonds, pi bonds, lone pairs, and carbocations. So if we can get a grasp of all 4 of those things, we've got it made. All right, so we've got an awkward, grad school anecdote told. We've defined a whole bunch of terms for you. We've talked about formal charge and hybridization and all of that. Where we go from here now is going to be, we're going to start to get into how do we draw these structures? How do we represent them? Okay. I'm going to look at my notes really quick and make sure that I haven't forgotten anything. Yeah, so basically, let's see if I can, I'm going to erase a little, no, I'm going to leave all this up. So there's a couple of things that we've talked about already, and they all relate to this, right? And so, nope, now I got an eraser. Hybridization. So the stuff that we talked about at the end of the first video is all about these 2 things, right? So hybridization feeds into sigma bonds and pi bonds, and formal charge feeds into lone pairs and carbocations. Right? And so we're going to use these 2 tools now to help us figure out where the electrons are. All right, I think that's enough for this video. Oh my gosh, we're at 12 minutes. So that's definitely enough for this video. So in the next video, we'll start to get into drawing structures and how do we represent organic molecules on the page. See you then.